In this presentation, we're going to be looking at low ambient conditions and how that affects the refrigeration equipment, and then what can be done about it. Condensers and low ambience. Low ambient is considered any time the air is entering the condenser below 60 degrees Fahrenheit. What is the problem with low ambient? It lowers the condensing temperature. It lowers the head pressure. It lowers the pressure to the metering device. So now instead of having a higher pressure to push the refrigerant through the metering device, we now have a lower pressure, which is going to create a problem at the metering device. The lower pressure drop across the metering device will starve the evaporator of refrigerant. So instead of having maybe a 100-pound pressure drop, a PD, across the metering device, it may drop to 50, 60, 70 pounds, and the effect is starvation of the evaporator, resulting in less cooling. Therefore, we have the compressor running longer to do the same job because the system is less efficient. The solution is to keep the head pressure up by using low ambient controls that will deal with the head pressure. So let's take a look at the head pressure control. There are three common methods. One is to turn the fans on and off. The second method is to use dampers, and we're going to look at that, is to limit the amount of air getting on the condenser. And a third one would be to actually flood the condenser so that there is less space in that condenser for effective removal of heat. Let's look at the cycling of the fan first. When the head pressure falls, the fan shuts off. So we're going to put a device on there so that when that head pressure drops, the fan will shut off. When the fan shuts off, the head pressure is going to rise and the fan is going to start again. Here we see a system using a fan cycle control as we work through this process. Here we have an R22 remote condensing unit. The ambient is at 78 degrees. No problem because it's above 60 degrees. With a 78 degree ambient plus a 30 degree TD across the condenser, we're looking at a 108 temperature on the condenser, which gives us a 220 pound head pressure, as shown here. Now, when the ambient drops to 60 degrees, let's see what happens. At 60 degrees plus 30 equals 90 degrees. Now the head pressure drops to 168 pounds. So we drop from 220 pounds to 168 pounds. Pretty significant drop in pressure relative to looking at the meter device and having it being forced at refrigerant through that restriction called a metering device. And now we see on the gauge the pressure drops to 168 pounds. At that point in time, we need to be seriously looking at installing fan control. And inside that fan control, you'll notice that it looks like, at least electrically drawn, a low pressure switch. But if you look at the numbers on the scale, it is a high pressure switch. So it really is a high pressure switch that operates opposite of a high pressure switch. It looks like a low pressure switch operating on high pressure. Therefore, we call it a reverse acting HPC. It does the opposite of what you would think it would do. Now here we see the wiring going to the fan. Normally the wire comes directly to the fan so that when the compressor is running, the condenser fan is operating as well. But we need to rewire the unit. And we're going to take one of the wires coming in, the hot wire coming in, go through the switch, and then go to the fan. So now the fan control, the reverse acting HPC, is in control of the fan. If the pressure falls, as it will under low ambient conditions, notice the switch will open and the fan would stop. Once the fan stops, there is no more air across the condenser, the pressure will rise and the switch will close and bring the fan back on. Okay, we need to set the fan control so that it operates correctly. And as I mentioned earlier, a fan cycle is a reverse acting HPC. When the head pressure rises, the contacts close, and when the head pressure drops, the contacts open. So here is some rule of thumb for setting the control. You want it to cut out at a 90-degree condensing temperature. You want to cut in at a 110-degree condensing temperature. Cut out at 90, cut in at 110. Let's follow the following slide here and see what we're going to do about it. We're going to cut out at 170 psig. Now remember, the cutout is at 90 degrees, so 170 pounds reflects the PT chart of R22 at 90 degrees. It's going to cut in at 225 pounds because 110 degrees going to the PT chart for R22 would be 225 psig. And the differential we would adjust to 55 pounds then. Here we see the fan cycle control, and something peculiar you need to look at here. It says switch low event is high event minus differential. So the switch is going to respond to the low event equal to the high event minus the differential. So instead of saying cut out and cut in, this particular manufacturer chooses to use the terminology low event and high event. The low event would be when it cuts out, the high event would be when it would cut in. So it would be the cut in, low event, equals is the high event, the cut out, minus the differential. Going to be working with an R22 system. The high vent is what it cuts in at, and we want to cut in at 225 pounds. We want the low event, which is the cutout, to cut out at 170 pounds. Therefore, we would need to set the differential at 55 pounds. Moving on to the second of the three methods of controlling head pressure, and this would be the dampers. If we limit the airflow through the condenser, that's going to keep the head pressure up. And the dampers are going to respond to the head pressure or the ambient air temperature. So either way, we can control the dampers via the head pressure or through air temperature, the ambient air temperature. Here's a remote commercial condenser, and it has multiple passes in it, meaning it has actually 3 coils in this condenser with 2 fans. Separate system circuits, 3 of them. So there's 3 condenser in this one housing. Here's the condenser with shutters on it. We have an ambient air of 95 degrees. When we have an ambient air of 95 degrees, the shutters are going to be fully open because the head pressure is going to be up and everything functions normally. Here we see the refrigerant coming in at 325 pounds, and that's equal to 125 degrees on a 404A system. So we have a low temperature freezer application here with our 404A. At 325 pounds, our 404A is going to be 125 degrees. So the refrigerant is going to go through the condenser and it's going to condense. And that pressure is going to be pushing on that cylinder there, that piston, and the mechanical linkage is going to drive the shutters open. Now when the ambient temperature drops, notice we've dropped now to 50 degrees. Now at 50 degrees with that colder air coming across the condenser, the pressure is going to drop to 175 pounds, which is equal to an 80 degree condensing temperature for 404A. And notice what happens. We do not get the condensing properly, and the pressure is going to drop, and then the linkage on the shutter blades will all move together as that piston moves back in its sleeve, and we will get an airflow reduction. Now, once we get an airflow reduction, that's going to raise the head pressure back up, and you'll notice the flow through the condenser now is back to normal. And it's going to come back up to 205 pounds at a 90-degree condensing temperature. When I say normal, it's never going to get back up to what it would be on the 95-degree day, but we certainly are keeping the head pressure up at 205 pounds. Now, as the ambient drops further, we're looking at a 0-degree day. We need refrigeration equipment operating on a 0-degree day. Notice the pressure on the head has dropped to a whopping 70 pounds. That gives a 30-degree condensing temperature for R404A. So all of a sudden, it makes this condenser look like it's an evaporator with a 30-degree temperature on it. That can't be. So notice the condenser. The condensing process occurs very early on in the condenser because of the pressure being so low. And the piston now will move further back into its sleeve, bringing the shutters fully closed, and then we have no airflow except for what leakage might be coming around those dampers going to the coil, and that will now bring the head pressure back up. Certainly not to what it would be on a 95-degree day, but that's okay. 205 pounds is certainly a lot better than what we had left it. Now we will be able to get the proper amount of refrigerant through the metering device and into the evaporator, and the system will be running more efficiently. The third of three is what is known as a flooded condenser, and it has the same effect as overcharging the unit. We use a head pressure regulating valve, an HPR valve, and what it will do is restrict the liquid flow out of the condenser. So we're actually putting a restriction on the outlet of the condenser so that the liquid can't get out of the condenser as easily. That will keep the head pressure up because we can't get the liquid out of the condenser. And because we have to have this refrigerant flowing, the valve also then has to be designed to bypass some of the hot gas to the receiver. Now, when you bypass some of the hot gas to the receiver, that will also assist in keeping the head pressure up. So let's take a look at the system using this head pressure regulator. We're going to look at a standard operation first where the ambient is above 60 degrees. You'll notice that coming off the discharge line of the compressor, we pipe it to the HPR. Then coming out of the condenser, it's piped to the HPR. So you have a port that is connected to the discharge line. You have a port that's connected to the condenser, which would really be the beginnings of the liquid line. And we have a port which goes to the receiver, 3-ported valve. If it's above 60 degrees, we're going to be looking at 210 pounds on the discharge line, 210 pounds in the condenser, and 210 pounds on the receiver side of this valve. Now, what happens when we get below 60 degrees? Let's say we have a 50-degree ambient. Notice the piping. We have a 50-degree ambient plus 30 degrees gives us an 80-degree temperature on the refrigerant, which would be 145 pounds. So the valve's going to back up the refrigerant. It's going to put a little guy in there and he's going to say, stop. We don't want all that refrigerant coming through here. And when we back it up, notice that the condensing process can occur properly and the pressure will rise because we backed up the refrigerant into the condenser and the pressure goes up to 180 pounds as shown here. See, even though we have a low ambient of 50 degrees, we can raise the pressure to 180 pounds by not allowing the refrigerant to come out of the condenser, or at least not as much. Now the valve is going to mix the liquid coming out of the condenser with the hot gas coming from the discharge line. Take an inside view of this HPR. We have an HPR rating at 180 psig. Now that is determined by the manufacturer. When you buy the valve, you would buy the valve based upon the head pressure you want to maintain. The valve is inactive above 180 psig condensing temperature. In other words, it's basically like it doesn't exist in the system. In our example, we're going to be looking at 210 psig condensing pressure. That's higher than the valve rating. So the HPR will not bypass any hot gas through itself to the receiver. All of the liquid from the condenser will go directly to the receiver. So here we have 75-degree ambient plus 30 gives us a 105-degree condensing temperature. For R22 would be 210 pounds of pressure. So we're coming from the condenser with liquid at 210 pounds. Our discharge vapor from the compressor is at 210 pounds, and notice the valve seat is closed, so there will be no vapor on the discharge line coming into the valve. So whatever's coming in from the condenser is going to go out to the receiver. And what we see here is the 180 pounds in this power head is less pressure than the 210 pounds coming from the condenser. Therefore, the valve will be pushed, literally pushed, closed. Under normal operation now, the liquid from the condenser will go directly to the receiver. And it will be at 210 pounds also. So everything is in equilibrium at 210 pounds. As the ambient falls, the pressure is going to fall. The following slide shows how condensing pressure falls as the ambient temperature falls. Here our ambient drops to 50 degrees, and 50 degrees plus 30 degrees equals 80 degrees. That's a 145-pound pressure on an R22 system. We have discharge vapor from the compressor. It's at 145 pounds. We have liquid coming from the condenser at 145 pounds. And going to the receiver, we see 145 pounds. What's going to happen is the 180-pound valve is more than 145-pound condenser. So the pressure in the head here is greater than the pressure on the liquid line. So the valve will go into its activation mode. It will start to stroke. The HPR restricts the condenser outlet. This will back up liquid into the condenser, and the head pressure will go back up to the 180 pounds, which is what the valve will continuously monitor and modulate at. The valve allows some gas and liquid to pass. The mixture, which is at 180 psig, goes to the receiver. So the valve's going to back up the refrigerant into the condenser. Notice the valve has been pushed downward, opening that seat. So now we're restricting the liquid coming back from the condenser, and that restriction is going to increase the pressure to 180 pounds because it can't get out of there as easily. What's going to happen on the discharge line is going to go up to 180 pounds, and we're going to see then that we're getting some discharge gas coming in to the valve and liquid from the condenser coming into the valve, and that mixture now will go on to the receiver at 180 pounds. This concludes the three methods of controlling the head pressure based on ambient.